所以今天以后我们还有2星期，在1天最后一天是5月1号。那这个是2星期后就是4月28号，你们要给我，然后我那个周末就改了，所以你们5月1号就可以全部那个知道你们的成绩大概大家都会，大部分都是 A 的，我想你如果有做的这些习题那你们如果是要跟我谈话的话，我普通应该下午在，可是不一定所以最好还是就写个电子邮件给我那这样子我们可以就做个 appointment 对不起，我哪一个同学刚刚来？你想想Okay, so now today I would like to prove the equivariant, the Borel localization theorem, that will allow you to determine the ring structure of an action of equivariant cohomology, because it compares the equivariant cohomology of a G space with the equivariant cohomology of the fixed point set. Okay? But in order to prove that theorem, I need a few preliminary facts that I won't prove, so I will just state them. Okay? So I will first talk about the equivariant tubular neighborhood theorem, and then the equivariant Mayer-Vittora sequence. Okay? So these are both equivariant versions of standard theorems in differential geometry and differential topology. Okay? So we first need the equivariant analog of a vector bundle. Okay? So let me first define an equivariant vector bundle. All right, so a vector bundle is G equivariant if well, the definition is very natural, so it's what you would expect, right? What would you expect an equivariant vector bundle to have? Like, when would you call a vector bundle G equivariant? Yeah, so there's a G action on what? Yeah, there should be a G action on the fiber, right? And the fiber of a vector bundle is a vector space. So that G action should be a linear transformation. Well, if there's a G action on the fiber, then there's a G action on E, right? Because E is composed of fibers. And but that G action, if you require that it sends a fiber to itself, that's too restrictive. Okay? So you should allow that G action to send a fiber to another fiber. And therefore, there is an action of G on M also. So the first condition is that both E and M are G spaces. Let's say left G spaces. And pi is G equivariant. Now, if pi is G equivariant, then that means if you have a fiber above X, right, and X goes to GX, the fiber above X should go to the fiber above GX. Okay? And so that map should be linear. Yeah. So G acts on each fiber linearly. Okay? So i.e., if you take the fiber at X, the fiber of E at X, it goes to the fiber of E at GX. And that's a linear transformation. For all G in G and X in M. Okay? Yeah. So EX is the notation for the fiber at X. Okay, okay, so that's an equivariant vector bundle. Now, whenever you have a G equivariant map, right, that induces a map in the homotopy quotients. So if pi from E to N is a G equivariant vector bundle with fiber V, then the induced map in the homotopy quotients is an ordinary vector bundle with the same fiber. So, well, this is pretty straightforward. It's just checking the definitions, and it's done in the book, so I'm not going to go over that. Pardon? Oh, NG, that's right. Yeah, thank you. Okay, now I'm going to define a tubular neighborhood. Tubular neighborhood. Okay. So now if you have a manifold, well, let's say the blackboard is a manifold, and you have a submanifold S. So then a tubular neighborhood is an open neighborhood. It's like a tube around S. So a tubular neighborhood looks like that. Okay? And it has a structure of a vector bundle over S. Okay. So with S as the zero section of the vector bundle. Okay? So that's the definition of a tubular neighborhood. It's something that looks like this, like a tube, and so it has the structure of a vector bundle over S. A tubular neighborhood of a submanifold S in a manifold M is an open set U, containing S. So it's an open neighborhood of S such that so U has the structure of a vector bundle over S with the inclusion being the zero section. Okay, and there's a theorem called the Equivariant tubular neighborhood theorem. Just a minute. How does this go? There's a screen there. The screen, should it go up first? Now, is the screen supposed to be down there like that? Or maybe I shouldn't use. I think the screen should. Let me see if I could use this one. Maybe I won't use the bottom one. And it looks like it cannot go up all the way either. Okay, so I'll just use this one. Okay, and not use the bottom one. Yeah. Now, the tubular neighborhood theorem in differential geometry says that a compact submanifold always has a tubular neighborhood. Okay? And moreover, that tubular neighborhood is isomorphic to the normal bundle of S in M. So, yeah. So, if S in M is a compact submanifold then S has a tubular neighborhood U such that so U has a structure of a vector bundle over S, right? So U over S is isomorphic to the normal bundle N of S in M. S in M. Yeah. So this theorem, it's a little messy to prove, but in my book I just give some general ideas, and then I refer to Spivak's book, where he has all the details. Okay? But we're just going to assume this from differential geometry. Every compact manifold has a tubular neighborhood, isomorphic to the normal bundle. And there's an equivariant version. So the equivariant tubular neighborhood theorem. So then in the equivariant version, both S and M have to be G manifolds. So in other words, M is a G manifold, and then S is a G invariant submanifold. Okay? So if M is a G manifold. Now, if I talk about G manifold, that means we're in the C infinity category, so G is a Lie group. Okay? So if M is G manifold, and S is an invariant, is a compact invariant submanifold. Compact G invariant submanifold. Then S has an equivariant tubular neighborhood. Well, I need to define an equivariant tubular neighborhood. Okay. So an equivariant tubular neighborhood of a G invariant submanifold in a G manifold is a G invariant open set S U containing S such that U has a structure of a G invariant equivariant vector bundle over S, with the inclusion being the zero section. Yeah. Let's make the definition first. Okay. So definition, an equivariant tubular neighborhood of a G invariant submanifold S in a G manifold M is a G invariant open set U containing S such that U has the structure of G equivariant vector bundle over S with the inclusion as the zero section. Okay? So it's the same picture as this, but everything is, but the spaces are G invariant, and then the maps are G equivariant. Okay? Okay. And then we have G equivariant tubular neighborhood theorem. So equivariant tubular neighborhood theorem. Right? So it basically says the same thing as the tubular neighborhood theorem, but now, S is a compact G invariant submanifold, and then S has an equivariant tubular neighborhood. So if S in M is a compact G invariant submanifold of a G manifold M, then S has an equivariant tubular neighborhood U such that U mapping to S is isomorphic to the normal bundle of S in M. Okay, so that's what we need to assume about a compact G invariant submanifold. Okay? And then the next thing I want to do is to prove the analog of the Mayer-Vittora sequence for equivariant cohomology. So, equivariant Mayer-Vittora sequence. Now, in the Mayer-Vittora sequence, you have a manifold and you have an open cover with two open sets. And it relates the cohomology of the manifold, the two open sets, and the intersection. Right? Now, in the equivariant version, then everything should be G invariant. Okay? The spaces should all be G invariant. So, so you have a manifold with an open cover consisting of two G invariant subsets. Okay, so let M be a G manifold. U and V, two G invariant open subsets. Such that their union is M. Then there is an exact sequence. Okay. So I picture it this way. You have a manifold M, and then you restrict it to the open subsets U and V separately. So this is a disjoint union. Okay. And then, okay, you can further restrict the cohomology to the intersection. So basically, you have an inclusion from the intersection into U and the inclusion from the intersection into V. And then you have the inclusion of U into M and V into M. And those inclusion maps will induce restriction maps in equivariant cohomology. So you have HKGN, okay. It restricts to HKGU plus HKGV. And then so something from here will restrict to the intersection. Something from V will also restrict to the intersection. So you take the difference. Okay? So this map is given by, say, alpha beta goes to, you restrict from U to the intersection. This is the inclusion of the intersection into U. So the pullback will be the restriction minus I of V. You intersect V star beta. Okay? So this is basically the difference map. Okay? And here is just the restriction map. So you have this in every degree. You have it in H K plus 1 also. And then here you have it in H K minus 1. Okay. All right. And in the Maya-Vittora sequence, there's a connecting homomorphism. So it goes from here up to there. And there's a connecting homomorphism from here to here. Okay? So you have a long exact sequence. Mm-hmm. I mean, it's exactly like this Maya-Vittora sequence in ordinary cohomology, but now we're using equivariant cohomology because all of these spaces are G spaces. Mm-hmm. Yeah. So I want to prove this from the Maya-Vittora sequence for ordinary cohomology. So the first thing that we need to prove is that if we have an open cover consisting of two invariant G invariant open sets, then when you take the homotopy quotients, they still give you an open cover of MG. So lemma, if UV are G invariant open sets that cover M, G manifold M, then UG and VG are open sets that cover MG. Okay. So now, okay. So first of all, I want to prove that UG is a subset of MG. So since the inclusion from U into M is G equivariant. See, both are G spaces, so I is G equivariant. IG. Okay. So there is a map. There's an induced map. And, it's a general property of equivariant maps that if you start with an injective map, then the induced map is injective. And so that says UG is a subset of MG. And now you want to show that it's open. Okay. So by definition, now UG is EG cross U, and then you divide by the diagonal action, right? Yeah. And since EG cross U is open in EG cross M, so in the quotient topology, a set is open if and only if its inverse image is open. So since the inverse image is open in EG cross M, so we know that UG is open in MG. Right? All right, so yeah. So similarly, VG is an open subset of MG. And then now, so similarly, of MG. Okay? So now we have two open subsets of MG, and then we now want to prove that they cover MG. Okay? So claim MG is equal to UG union VG. All right, so so we take the point in MG. Now a point in MG looks like this, right? EX is an equivalence class where EX is in EG cross M. And so X, so X is in M, which is U union V, and therefore X is in U or V. So if X is in U, then EX is in UG. If X is in V, then EX is in VG. Okay? And so therefore, EX is in UG union VG. Okay? And yeah, so that proves that MG is equal to the union. Okay? Yeah. So starting with 2G invariant open sets that cover M, we get an open cover of MG, and so we can apply the ordinary Mayavi-Torres sequence to this open cover, UGVG. Okay. But then you have to look at the intersection. So we need to prove that UG intersected with VG is U intersected with VG. Okay, so let's see. Let's try to prove this. Now, let's see. What is obvious? What? U intersect G. U intersect V. It's contained in U. And this is G equivariant and injective. So that implies that if you take the homotopy quotient, right, this is injective. And similarly, U intersect V, G is a subset of VG. And so U intersection VG is included in UG intersect VG. Okay? So that proves one direction, this direction. And then we have to prove the other direction. Okay, so let EX be in UG intersect VG. Okay. Then EX is in UG. So now, actually, EX, it could have other representatives, right? It could also be EG G inverse X. Yeah. So what we know is that EG, there's some representative that's in EG cross U for some G. Yeah. However, U is G invariant, so that says X is in U. Yeah. Yeah, right. And therefore, yeah, so similarly, the same argument will prove that X is in V. So X is in the intersection. X is in the intersection. And so EX is in U intersect V G, the homotopy quotient. U intersect V. And so this proves the other direction. UG intersect VG is U intersect VG. Okay. All right. So now we apply the usual Meyer-Vittora sequence to the open cover UV. No, not to that open cover. We apply it to the open cover UGVG. Of MG. Right? And we get HK of MG restricting to HK of UG plus HK of VG restricting to HK of UG intersect VG. And then HK plus 1 of MG. Okay. And this comes from HK minus 1 of the intersection. So the usual Meyer-Vittora sequence will give us this exact sequence. But now, you see, this is the equivariant cohomology of M. This is the equivariant cohomology of the intersection. This is the equivariant cohomology of U. And the equivariant cohomology of V. Okay? And this gives you the equivariant Meyer-Vittora sequence. Okay? So we apply the usual Meyer-Vittora sequence to this open cover. To get the equivariant Meyer-Vittora sequence. Okay? Yeah. So we have basically two major tools for computing equivariant cohomology. We have the spectral sequence of a fiber bundle, because the homotopy quotient is a fiber bundle over BG. So we can use the spectral sequence to compute equivariant cohomology. And then we can also use the Mayer-Vitora sequence to compute equivariant cohomology, from the equivariant cohomology of open subsets. And so that's what I'm going to use in order to prove the Borel localization theorem. Now I have about, now I started at 12:20, right? Yeah. So I have just a few minutes. And so in those few minutes, then I will just prove some general theorems about actions. Maybe just one. So now what I want to show really is that if a circle acts with no fixed points, then the action is locally free. Okay? So if S1 acts on M with no fixed points, then the action is locally free. Okay, so let's see. So why is that? If there are no fixed points, that means, what can you say about the stabilizer? Yeah, so it has to be a proper subgroup. But it can't be the whole group. If it's a whole group, then the stabilizer would be S1, and then you have a fixed point. So since there are no fixed points for any x in M, the stabilizer of x is a proper subgroup. Okay. Now, a proper subgroup, and in addition, the stabilizer is always closed. So because like if G is a limit point of the stabilizer, then there's a sequence in the stabilizer that converges to G. And because the action is continuous, that means Gn dot x will converge to G dot x. Gn dot x is x, because Gn is in the stabilizer, and x will converge to x. So by the uniqueness of the limit, g dot x is x. Okay? So g is in the stabilizer of x. Okay? Yeah. So that proves that the stabilizer is a closed subset. So it is a subgroup and it's a closed subset. So it's a closed subgroup. And a closed subgroup of a Lie group is a Lie group. A closed subgroup of a Lie group is a regular submanifold. So thus, as a closed subgroup of a Lie group, so stabilizer of X is a regular submanifold. So if it has dimension now if it has dimension 0, then locally it looks like this, right? It's a submanifold dimension 0 in a manifold dimension 1. The circle has dimension. So locally it looks like that. Therefore, it is discrete. Okay? And that means the action is locally free. The stabilizer is discrete. And now if the dimension of the stabilizer is 1, then yeah. Well, then locally, so the stabilizer is, it's not this, but it's this. Homeomorphic to an open interval in R. And therefore, that says that every point of the stabilizer has a neighborhood like this. So the stabilizer is open in S1. Okay? Because it's locally, if it has dimension 1, it's locally an interval. And so it isn't open in S1. Now, how do you get a contradiction from this?
Stabilizer is both open and closed.
Yeah, then the stabilizer is both open and closed. But S1 is connected, so that means it has to be S1 or the empty set. It can't be either because it always contains the identity. But if it's the whole thing, that contradicts the fact that it's proper. So since S1 is connected, stabilizer of X is the empty set or S1, so both are impossible. Okay? So the only possibility is that the stabilizer has dimension 0 and it is discrete, and therefore the action is locally free. All right? Yeah. So, yeah, that's stabilizer of X is discrete, and the action is locally free. Okay. Okay, so we're going to take a 10-minute break, and then in the next hour we will prove the Borel localization theorem. Now, who didn't get the final problem set? Yeah. Okay, so the final problem set is due in 2 weeks, and right now maybe you don't know how to do some of the problems, but we'll be doing some examples and covering some of the theory. So then, I think by the end of next week you'll be able to do all the problems. Okay? Yeah, and so you really have a week to work on them. But right now, I think you can do a couple of the problems now. All right, so let's take a 10-minute